Good morning, everyone. I need to get to bed. I got off work a few hours ago. Oh, 3 hours ago, almost. A little over 3 hours ago. Got physical therapy tomorrow. Ugh. Back's killing me. Just took some pain meds. Now, when I uploaded this tutorial the other day, when I wrote that code for that function, the get address function, when I was writing, I was like, "Oh, this is bad. I should fix this." As a rule, your function should only have one return, right? And then you should have a series of paths to get you to that return throughout it. And you should return a variable that you modify. I say this because it's cleaner looking and it's easier. Well, it's not always easier to follow, depending on how people name their variables. I wouldn't say that there's really anything wrong with returning mid-function, but things like this can occur when you forget certain things have to happen, and if you return before they can happen, they won't happen. So, TDJ says, your free won't hit unless pattern isn't found. This is very true. So, if we're successful in doing our modification, we aren't going to free the memory that we allocated. And we see that here, where we are allocating our space, the size of the image, which is X number of bytes, I don't remember. We read it one time, so one time we read this number of bytes, which is almost 14 megabytes. Not quite, almost. And then we loop through and we search. If we don't find it, we break. If we find it, oops, I've fixed this already. Let's unfix it. Return 0. Okay. So if we do find it, we're instantly returning the address. Now, the problem with that is this is never going to get ran. This free, not going to happen because we jumped out of this function long ago. And what that is going to do, if we run this, and I should have noticed this actually, because your program shouldn't, after the function is done, when you theoretically freed the memory, it shouldn't still be using almost 4 megabytes. It's like 13.3 megabytes, a little over. Yeah, that's bad. So let's fix it really quick. And what you do is do dword retval equals 0. Initialize it to 0, not found. Why dword? Well, because our function returns a dword. Instead of returning here, set retval equal to the address, and here just return, retval. So cool. We need an equal sign here. There we go. Now, the problem with this here is we find it, we set it, but we keep searching, and it's not going to break until the next false. So we actually need to add break right here. Well, if you're going to break, why not just return? Well, we could do a free and then do a return, but that's bad. You shouldn't write more code than you have to. We shouldn't write free multiple times, and here's why. As a rule, for every malloc there needs to be a free. Now, if we allocate once and then we have 2 frees, someone else could come in, especially if it's not commented, and be like, why is this being freed twice? And be like, I'll just get rid of this one, and now you have a memory leak. So you should be able to do it one time, and that's why I say you should have one return for your functions, not multiple returns. You should have one, and a series of paths that get you there. But again, it's not necessarily bad to have multiple returns for a function. This, like JavaScript programmers or a lot of the web, like PHP, stuff like that, it's really common to enter a function and then based off of data do, you know, if return. It's a thing. So now if we compile this and we run it, Control Escape, blank is only taking up 612 kilobytes, as it should. You know, the program itself is only 9 kilobytes. It should never take up even a megabyte. So, excuse me. Problem solved. Now, we have another comment on here about the way that we find that address. And it's, I believe you could still read the memory in chunks by simply having a loop that will read the amount of bytes in the mask. This is true. But if we come in here and we change this to int a equals 0 while like this, and then we come down in here and we have our breaks, and before we exit we do a plus equal strlen mask, and over here we don't need an a here. Mem section is always going to be the same. We don't need to use malloc because we're only going to do it, we're going to use a set amount that's rather small, so we have that much on hand. We can do mem section strlen mask, and then our read can't happen here. It has to be in our loop. Now, there's a problem with that. Read process memory is kind of a slow function, like kind of a really slow function. Anytime your process has to look in another process, a lot of magic has to happen, and well, it's costly. So this actually has to, of course the comments aren't going to match up anymore. What? Okay, well, my thing apparently had a hotkey set up there. There we go. Okay, sorry about that. Now, of course, our comments aren't going to match up anymore because we aren't grabbing all of that. We're grabbing start scan plus A, and we're reading it into the address of mem section. And we're not grabbing this, we're grabbing strlen mask. Of course, we could define strlen mask as a, well, the strength length of mask into its own variable and just reference the variable, and we wouldn't have to call this function within a loop, and that would cut down. You know what? Let's do that. Let's go ahead and get rid of that. And up here above it, we'll even use it up here. We'll do int num bytes equals num bytes. Now, so now we don't have to call that function 800 times, or it's a lot more than that. You'll see. There we go. So we're going to keep doing this until a is less than, or while a is less than the size of the image. Now, we don't want to keep checking for that either, and we already have a variable for it, so I don't know why we weren't using this before. Let's go like this. Now, we don't need to do a D word because a is an int. It doesn't matter. D word is synonymous for unsigned char, unsigned int. I don't remember. It's something. I forgot. There. Now, so this is gonna loop through our mask, each one, Break if you don't find it. We're going to have the proper return here. Break if you do find it, but set the ret val first. And it is still going to be start scan plus A plus I. That's good. That's fine. I'm good with that. And we're going to increment by our mask. So we're not incrementing by 1. We're not going to move each byte. Now, this you would have to be incredibly lucky for it to work. As I explained in the comment, if you have there we go. If you're looking for 5, 6, 7, 8 and the string is 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, and you're grabbing 4, first you're going to grab 1, 2, 3, 4, cool, doesn't match. Then you're going to grab 5, 6, 7, 8, matches, we stop, we're good. But if the string is 1, 2, 5, 6, 7, 8, 3, 4, 9, A, B, C, you're going to grab 1, 2, 5, 6, not going to match. Then you're going to grab 7, 8, 3, 4, not going to match. Then you're going to grab these. It's not going to match. You're going to run out. You're not going to find it. It just won't work. And I'm willing to bet that that's exactly what happens. Let's see. Oh, this doesn't need to be like that anymore. There we go. Compile. Okay. That worked. Let's see if it finds it. Let's see if it runs. I could have screwed something up. So it didn't find it. And it had a little bit of a pause to it. Now, let's increment by 1. A++. So if we break, we want to do this addition after this, in case we do find it. We don't want to do it at the top. So now we're going to increment by 1, and each time we're going to be grabbing the number of bytes our mask is long. Now you look at the size of this, it was 9 kilobytes, now it's 53. But the code looks smaller. But this is being called so many more times. Now, we wait. And wait. Keep waiting. And sometime soon. Whoa. If I look at the camera, my glasses, the glare on my glasses is the same color as my green screen. Oh, look at that. We found it. We could have popped a bag of popcorn almost. Okay. So we did find it, but we didn't grab this number of bytes of memory. No. That's what we grabbed if we did it one time with one read all at once with allocation. Roughly, 13.3 megabytes. Now, let's go ahead and comment that out because that's false. We know that's false. Now, let's set a variable int num reads to 0, int bytes read to 0, and let's find out. So every time we read, let's do num reads, oops, that's not gonna work, plus plus, and let's do bytes read plus equal num bytes. And yeah, these variable names aren't the greatest, I'll admit. And then before we return after we free, let's go ahead and printf number of reads number, or no, what, total bytes read %e, excuse me. And then we have, what was it called? Num reads bytes read. Now, let's go ahead and run that again. Compile, cool. Wait, go make yourself some popcorn because it's gonna be a while. I have a drink. So how's your day been? Mm-hmm. Oh, I'm just waiting to find an address. Yeah, I mean, it's fine. Oh, there it is. Now, we did 13,611,008 read process memory calls. Ooh, focus. Thank you. And we read, let's just bust out the calculator here. That's not a calculator. Clear. Paste. Divided by 1024. Divided by 1024. We read 519 megabytes worth of data. That's a lot more than 13.3 megabytes. And you see why it was slow. So imagine we had that memory leak in here still where we don't break and we just return. But we know that this isn't going to get hit, so X, we're going to put that up here before we return. And that's fine. Now, there's a plus to this because we're only allocating that space one time. Oh, we left it running. So this isn't actually going to, this doesn't even need to be here anymore, really. And it's going to take just as long and it's going to be just as small. And we can, as evidenced by, it's not growing. But look at that CPU. Woo! Didn't take quite as long. Weird. But yeah, let's actually do a malloc in here, memory allocation. And let's do it in the loop. This is, you would never do this, ever. Mem section equals malloc numbytes. Oh man, this is really bad. Void, oh what? What did I do wrong? Valid conversion from void pointer to char point. What? Oh, right. We would do mem section char pointer mem section. It is not like it. So let me reference my code. Mem section goes char. Oh, you just have to cast it. Silly me. Compile. Oh, right. We have to cast it because I used char instead of void pointer. Wouldn't have to cast it if you just change it. So now if we run this, we're going to see that it takes forever and we can watch our leak grow. There we go. Oh, found it. Look at that. We read less bytes that time. That's weird. I wonder why that first time. I'm not sure. But yeah, you wouldn't do that. That would be a bad idea. But if we go all the way back to the original fix. Oh, too far. Rep val equals 0. Rep val. There we go. Compile, it's still running, so I gotta close that. Compile. Oh wow. I ran it a lot. Remember that? That was a thing. Compile. 9 kilobytes. Cool. Instantly. Instant. Got that. That's what we want. We don't want none of that. Blank. 612 kilobytes. Good. So, good catch. Can't believe I missed that. Can't believe I didn't go back. And you know, I wanted to demonstrate that mask grabbing, because you don't need to grab all that multiple times. Bad idea. It does work, but it's not efficient. Although if you got lucky and could grab in increments of the mask, one after the other, you would cut down lots of time, but it wouldn't work for every mask ever. You might be able to make it work for one by evenly dividing, but no, just don't do it. Do it right. It's a lot easier to just go, hey, I need to search this chunk of memory, give it to me. Just do it byte by byte. It's a lot quicker. Serial is, and this is how you look at it. We used to have parallel ports, and we used to have hardware that, like video cards, they talked in parallel. So the memory bytes would send many all at once, but the problem was they had to get there at exactly the same. All of them had to get there at the same time. Otherwise, you had issues, big issues. And then they realized, we're sending 32 bytes at a time, and we have to wait for it to get there before we send the next one. It's really slow. And they realized, if we send it one at a time, it doesn't matter how fast we send it, because, well, it's going to send one, receive one, send one, receive one. You don't have to wait for all of them to get there to process. Unless you could make parallel get there at exactly the same time and process them all at the same time. So with serial, it gets one, does the whole process. Do it. Just read it into a buffer, do it. And you could do it as fast as you can. Serial, faster than parallel, every time, hands down. Now there is a point where parallel could be faster, but not efficient at all, because the CPU required to process all of that at once to where you could continually receive more would be, if you did the same thing with serial on that same processor, you could make it even faster. So it's, hands down, same idea here. Serial, one byte at a time, serial, faster than parallel. Whole mask, really not parallel, but it kind of the same idea. Anyways, video's long enough. Thanks for watching. Thumbs up if you like. Don't do that. Just ignore this one. If you don't like, I don't care. Really, I don't care. Thumbs down gets attention too. Like I say, any publicity is good publicity. On a side note, myself, my friend Casey, my friend Kevin, we started another channel. There's 30 some videos up, but nobody watches them. Partly because, But basically, we get together every Wednesday night around 8. We live stream us playing some game or multiple games. We're called Unexceptional Gamers. We don't claim to be pros. We don't claim to be good. We claim to be better than average, but sometimes worse than average. You could say mediocre. The YouTube link for that, of course, is youtube.com/unxgamers. That's UN, the letter X, gamers. If you want to watch on Twitch, it is twitch.tv/unexceptionalgamers. Kind of long, but it sticks. Unexceptional. Hey, you guys see those unexceptional guys? Yeah. Okay, anyways. There is that. If you want to tune in, watch us play some games, have fun, just sit back, go ahead. Pass it on. And again, thanks for watching. Next video, this comment at the bottom here, take the calculator, get the value that should be returned as an answer to a console, and return something else. We're going to do it. First, I got to find a 32-bit program, or a 32-bit version of calc.exe, because mine's 64, but it's not hard to find. You just Google. index of calc.exe and look for one that's in a folder that says WinXP32. Nobody ran Windows XP64. Nobody. Okay, maybe somebody did. Anyways, have a good day.